So I think in the introduction I can be a bit brief. So let C be a curve, smooth projective curve, always smooth projective curve of genus G, say greater or equal to 2. Everything is over C, and maybe I should say this is joint work with Elham-Izadi, so this I forgot, joint with Elham-Izadi. Yeah, then for such a curve we can define the Jacobian. And yeah, this is a Jacobian, is a principally polarized abelian variety of dimension G. Principally polarized, and so we get a map from the modular space of curves of genus G into the modular space of principally polarized dimension abelian varieties of dimension G, just associating to C the Jacobian of C plus the polarization which is given by the theta divisor, Riemann's theta divisor. And Torelli's theorem says that this is injective. Tau is this map. Tau is an injective map. What I'm going to talk about is whether the same is true for Prym varieties. Okay, so let me recall what is a Prym variety. This is an étal double cover, 2 to 1. And suppose G of C, now we take G plus 1, so that we get into, because the Prym variety has dimension, then G of C tilde by Hurwitz's formula is 2G is 2G plus 1. Okay, so the difference is G now. And then again we define, we have the norm map. Let me recall this. Norm F is of JC tilde into JC, and so this is called the norm map. The connected component of the kernel of this is the Prym variety. So P equal to P of F actually is by definition the connected component of the norm map. This is called the Prym variety of F. And one can show that if you restrict the theta divisor to P, theta divisor of J of C JC tilde to P, this is twice a principal polarization, where psi is a principal polarization. So you get a principally polarized abelian variety, and you get a map, the Prym map now, from the modular space of étal covers of curves of genus G plus 1, double covers, 2 to 1 covers, into the space again AG. Okay, associating F of C tilde to C, you associate to this the Prym variety of F. Prym-Torelli problem is whether this map is injective. So Prym-Torelli problem is pi injective. And if not, where it is injective, or what's the degree, or whatever, right? This is Prym-Torelli problem. And then I mentioned already in the course, there's a theorem that it is generic injective. This is I'm a bit more precise. So in 82, Karnev proved the theorem, which I'm stating later maybe, for G greater equal to 9. Then same here Friedman and Roy Smith, also in 82, proved this for G greater or equal to 7, both non-constructive. Well, maybe I'll do this later. Welters, because I did not yet, proved in 85 for G greater or equal to 16, and then finally Debar gave a proof in 89 for G greater or equal to 8. And what is the theorem? That pi is generically injective. What does that mean? That means that the degree onto the image is 1. So I write just degree pi onto its image, of course, because this in general has bigger dimension. The degree onto its image is 1. And those both proofs are non-constructive. And these are constructive. Meaning that if you have given a general principally polarized abelian variety in the image, you can reconstruct the double cover. Okay, so these, and all 4 theorems have a different proof, different method even. I'm not talking about this. So let's come to negative results. In fact, the map is not injective. Let me recall the negative in the results. First, there is something of Boville in his thesis in 77, that for G greater or equal, lesser or equal to 9, pi is not injective. How does he prove this? He uses Ristilia's construction, which I maybe Ristilia's construction, which says the following, that if C is trigonal and you have a étale double cover of a trigonal curve, if and only if the Prym variety of F is the Jacobian of a tetragonal curve, which you construct from this, right, is the Jacobian of a tetragonal curve. And then one knows for G lesser or equal to 9, there are curves with 2 tetragonal coverings, right? For G greater or equal to 10, not anymore. This is unique, but for G lesser or equal to 9, there exist curves with 2 tetragonal covers. 4-to-1 cover, I write. Tetragonal is 4-to-1 covers of P1, then I have to write of P1 if I don't write tetragonal, okay? So, and then Boville showed, this is not difficult to see actually, it's just a remark in his thesis, this was his thesis. They give different 2-to-1 covers C tilde over C. If you follow this construction, they give two different 2-to-1 covers, which means that pi is not injective at these points. Okay? Then Donaghy came up with a tetragonal construction.
Oh, you're holding things upside down.
Sorry?
The razor was, you're holding it upside down.
Oh, I see. Sorry, yeah. I see. Okay. So Donaghy, tetragonal construction. This was in 81. and says given C tilde over C etile 2 to 1, and this is a tetragonal cover to P1, then the number of pi to the minus 1 of pi of P of F is actually greater or equal to 3. He constructs, out of this, he constructs two other tetragonal cover, and we will see later how, because this is what we are going to generalize, right? So yeah, and then he, since he couldn't see any method how to find different covers which go to the same point, he made the following conjecture. Actually also in 81, but you can find it also, it is still in the Encyclopedia of Mathematics, in the article of Shokurov in, I think it was 89, in this formulation here. Pi is injective on the set. So set of etile double covers, which are like this here, in R2G plus 1, where X has no G14. Meaning it is not tetragonal, it is not trigonal. If it's trigonal, you have also a G14 just at a point. It's not hyperelliptic. Okay?
C.
C, sorry, yes, sorry, that's that, yes. This is, I changed notation in my, yeah. C, thank you. Okay? Okay. Then first doubts about this came 2004 when Vera showed the following example. Sandro Vera showed that if C is a smooth plane quintic, a smooth plane sextic, then pi to the number of points of pi to the minus 1 of pi of P of F is greater or equal to 2, so it's not injective. Also in this case is not tetragonal, it's 5 to 1, quintagonal, or I don't know how do you say this, pentagonal actually, you say pentagonal, okay? But, I mean, if you look at this and these examples, then these curves plus these are exactly those with Clifford index less or equal to 2. So at that point when he proved this, everybody, or at least we thought that you just have to replace it, and I will explain in a moment what is the Clifford index anyway, but we replace this by Cliff of C less, is injective. Sorry, what did I write? Injective, actually not injective, right? So is injective on the set where the Clifford index is greater or equal to 3. All right, sorry.
Maybe
this.
Before was written, if you have not a G14, it is injective.
Yeah. So
the plane sextic generally has no G14. So
no, but it is of Clifford index 2. That's why we changed this to Clifford index greater or equal to 3, right? Let me explain the Clifford index. Maybe it's not so well known. Okay.
Okay.
Yeah. So we'll see this here. So yeah. So maybe I can erase this already. So
it was a conjecture.
That was a conjecture, yes.
Conjecture.
Yes, Donagi's conjecture.
Okay.
Sorry.
Now I understand.
I see. Yeah. So let
Now
me
you change the conjecture.
change.
In order to.
Well, actually, yeah. Well, I think at least we thought, and maybe everybody thought that this should be the conjecture, right? Okay. So Clifford's theorem let me recall the Clifford index, right? Clifford's theorem says that if L on C is special line bundle, meaning that H1 is different from 0 and H0, or H1 is positive and H0 also is positive. Oh well, we have only H1 is 0, then H0 of L is lesser or equal to the degree of L over 2 plus 1. Okay? This is best possible if you, this is best possible. Well, for example, H0 of O of the trivial line bundle is equal to, the degree of this is 0 plus 1. So you cannot improve, right? Also there are some canonical bundle and so on which have the same, no, not canonical, I mean hyperelliptic bundle and so on, which have the same, right? But moreover here you have that there exists line bundle of any degree, any degree lesser or equal to G minus 1 with H0 of L equal to 1. Right? So you cannot improve anything if you have this. So that's why, however, if one restricts to line bundles of this degree lesser or equal to G minus 1 with H0 of L greater or equal to 2, you get an invariant, which improves Clifford's theorem. Okay? So, however, maybe I write this, if one restricts, if we restrict to L with H0 of L greater or equal to 2 and degree lesser or equal to G minus 1, or which is equivalent to H1 of L greater or equal to 2 by Serre duality, it's the same, then we get an invariant of the curve, which is the Clifford index. Is the maximum, by definition, this is a definition, maximum of all numbers C such that H0 of L is lesser or equal to degree of L minus C over 2. So you get a better bound here. If you have a high Clifford, plus 1. If you have a high Clifford index, you get a better bound. But you have to restrict to those ones here. H0 of L greater or equal to 2 and H1 of L also greater or equal to 2. Then you get an invariant, and this is the Clifford index. Okay? What are small? The curves of small Clifford indices. So Clifford index of C is equal to 0 if and only if C is hyperelliptic. This is already contained in Clifford's theorem. If you look at Hartshorne book or so, then Clifford's theorem says not only this, with equality if and only if the curve is hyperelliptic, right? So the Clifford index of C is 1 if and only if C is trigonal or a plane quintic. And the Clifford index is 2 if and only if C is tetragonal. I mean here smooth plane quintic, smooth. Or smooth plane sextic. Right, so you exactly, this was the missing case here, right? In the, if you omit, yeah. Okay. This was the introduction. So at the beginning I forgot to write introduction. First section is introduction. The second section is now the setup. Maybe I should say what I want to prove. I want to give counterexamples to this with high Clifford index. Arbitrary high, actually. So Donagi's conjecture is completely wrong. And the problem then to really find the open set where the map is injective remains widely open. It's even more complicated now. the setup. So let y be an arbitrary curve, smooth, everything is only smooth curves here. Arbitrary curve of genus g greater or equal to 0, greater or equal to 0. Right? Then we take an étal. First of all, we take a 4-to-1 cover. Let's call this rho. 4-to-1 cover to y, and an étal double cover. So this is x tilde, an étal double cover to this. Okay, this is the starting point, right? In Donagi's case, this was P1. So there we have an étal double cover of P1, so a tetragonal curve. Then we take the fourth symmetric product of y, so divisors, positive divisors of degree 4, and take the induced map here, rho fourth symmetric product of x to 4. Okay. Then one can embed y into this. By how? By just associating to a point here z bar equal to x1 bar plus x4 bar if these points are just the fiber. If or where rho to the -1 of y, I mean this is a 4-to-1 cover, over this are 4 points with multiplicities. Right? So y to -1 of y equal to x1 bar up to x4 bar. Right? This easily seen in embedding.
Does it embed into the x?
No. We take the. Sorry, what did I do? Oh, I made a mistake here. Yes, sorry, this is completely nonsense. Sorry, I'm still not really awake. Here I have x to the 4, and then I take x tilde to the 4. Sorry. Yeah. Of course, I mean, this is nonsense. Coffee was not strong enough, maybe. Okay, then we take the fiber product. So we get a curve here, which we call C tilde. The fiber product. So this is a Cartesian diagram, and call this map F tilde. Okay. So what are the points of C tilde? So C tilde consists of all liftings of this here to that, right? Consists of all liftings x1 plus x4 in C tilde, in x tilde, such that xi goes to xi bar, I mean liftings of these here, right? And rho to the -1, I have to repeat this, rho to the -1 of y is just x1 bar, x4 bar. Since this is an étal double cover, every point has 2 pre-images. So this has, I mean, this here, this is as a divisor, as a point in here. This has 16 pre-images, so the degree of this is 16. So degree F tilde is 16. Okay? Now we have to make an assumption. Assumption on the covering, that the monodromy group of the cover x tilde to P1 to y factors through the Weil group, factors through the Weil group W of type D4. right? I can write it down, but it doesn't matter which group it is here. This is not, if we have here y equal to P1, this is automatic, right? In general, it's not automatic, but you have to assume it. There is also another case where it goes to W of B4. And in this case, we have a different situation. But if it factors here, like this, then this consists of two components. Okay? So let me write it down. Then, first of all, C tilde is actually the disjoint union of C1 tilde, disjoint union C2 tilde. And I'll describe this in a moment. Why? The involution, which in the course I called iota, which I call here dash, right? The involution dash on x tilde. So let me write it like that. The involution dash on x tilde induces an involution on C tilde. Namely, sigma, I call this, for C tilde in C tilde, just as, well, the points of C tilde were formal sums here, I mean sums in the symmetric product. You can associate, of course, those where you dash everything. Right? This is an involution. Okay? Then what is C1 tilde is just those points with an even number of changes, and the other one even number of changes here, and the other is with an odd number of changes. Okay? So an even number of changes, xi goes into xi prime. So in other words, if x1 plus x4 is in C1, then also x1 prime plus x2 prime plus x3 plus x4 is in there. And also this is in there. And the other component, an odd number of changes. Right? These are two components. Because this factors through this Weil group here, you stay in the same component if you do the monodromy. Okay? If you do a change. Okay? And this is automatic if y is P1. So that's why it doesn't turn up in Donagi's original theory. Okay? And moreover, if you see immediately that if you restrict sigma to C1 tilde and C2 tilde, it goes to an involution. Okay? Sorry, it's hot here.
May I ask a question?
Yeah.
Why you use D4 and not maybe simply A4?
Ah,
I don't see the...
no, D4 is so to say that it should factor, so to speak. It should factor. D4 comes from, it respects, so to speak, this covering, right?
Because there is a preferred of the...
Yeah, you have this involution. Yeah.
I see.
Sorry, I just...
I see.
It's too hot.
Nice.
Okay. So what I said already, this restricts to Ci. So this implies that sigma restricts to Ci tilde. Ci tilde I wrote, hopefully. Yes, Ci tilde goes to Ci tilde for I equal to 1 and 2. Okay? And let Ci, so this is an involution on this, let Ci be the quotient. Modulo sigma. Right? Then we need a lemma that we really have smooth curves, etc., under a condition lemma, which I'm not going to prove. This is due to Welter's for y equal to P1 and to a former paper of ours, I mean myself and Elham, together with Volker Strehl, for Iy arbitrary. And it says that if rho is simply ramified, but ramified, I mean in the P1 case, in the Donaghy case, I didn't have to assume ramified because every covering of P1 is ramified, right? So here we have to say but ramified should not be étal, right? But ramified. Then we get that Ci tilde is smooth and irreducible. And second, Ci is smooth and irreducible, while Ci tilde then also. Ci tilde to Ci, this double covering is étal. 2 to 1 étal again, and also G of, you may work out, this is G of X, right? So we have the following situation. We started with this X tilde goes to X and here goes to Y. Then we have here C1 tilde goes to Y as well, of course, because everything is over Y, right? All of these are étal double covers, right? All of these have genus G equal to G of X, right? And these are all 4 to 1 covers because the whole thing was 8 to 1. Okay, we started with 16 to 1, then, well, got down to, and actually, yeah, okay, yeah. So one has Prym varieties in these cases, and Donaghy's theorem originally was if this is P1, then the Prym varieties are isomorphic, right? And we will see that under these hypotheses they are also isomorphic, right? This is more general. Okay, so the result now. Next section. Third section. And the fourth section will be the proof. Okay. So we take a correspondence, S. A correspondence is a divisor in a surface, in the product surface. So this is the following. Z, all points Z equal to x1 plus x4, comma x in C tilde cross x tilde. Or I could write Ci tilde if you wish, right? All right. So maybe I work only in C1 now. So C, new notation, then I don't have to write the I and so on. C, new notation, C is C1. Could also be C1 tilde, similarly C tilde equal to C1 tilde. Could also be, well, that's right, Ci, right? Omit the I because I work only on one of them and show, we will see that the Prym varieties are isomorphic. Okay? Well, why divisor? If x is equal to xi for some I. This is a correspondence, meaning a divisor here in here, right? And any correspondence, effective divisor, any effective divisor here gives, according to the Italian mathematicians of the 19th century, gives a homomorphism of the Jacobian here to the Jacobian here, right? So let S be the corresponding homomorphism, the associated homomorphism. How does one associate a homomorphism? The elements here were line bundles, which you can also describe by divisors. So divisors are sums of points, right? And you just take the image of the points which correspond, which I will write down later, which corresponds to, so these points here correspond several points here, and you take some of those. Then you get endomorphism, homomorphism in this case, okay? And then the theorem is S of JC tilde to JX tilde induces, not by restriction, but induces an isomorphism. I should really write induces, and we'll see how in the proof. An isomorphism of principally polarized abelian varieties. P of C tilde over C, well, recall this is Ci tilde. Xi is the principal polarization here, to P of X tilde over X psi. This is not good. Maybe this is a different psi, of course. Well, maybe here I write, then I have Ci here, right? Okay. For I equal to 1 and 2. And then I think I omit these again. Yes, I omit these. No, I don't. Okay. So, yeah, first of all, why does this, I have to say something about this, some remarks, and then we'll prove this. According to time. Remarks. First of all, if y is equal to p1, this is exactly Donagi's tetragonal construction. This is Donagi's tetragonal construction. There are two proofs. First, by Donagi, but not in his original paper, but in 92. He wrote in this paper in 92 that people, in his original paper, he didn't give any proof, not even a hint. But then he said here, he writes here that people urged him to give a proof. So he gave a proof in 92 by degeneration, right? By degeneration. So he degenerated, well, took degeneration techniques. And second, there's a second proof using theorems of Boville and Welters. And this you find actually in our book in 92. Okay? Both proofs do not generalize. Otherwise, one would have seen this earlier, right? Both proofs do not generalize. Because, for example, here, if you take this, you have also to degenerate y. And then the singularities you get here are too complicated, so that the Jacobians are not anymore, I mean, they are very general then. Not even semi-abelian or something. So it gets too complicated. That doesn't work. Also, this proof doesn't work. The theorems here are just not correct if you use this. Okay. So we have to have a third proof. So, and in fact, our proof is then a third proof, even in the Donagi case. And I hope to convince you that it's simpler. Well, you don't know the other ones, but it is simpler than the original proofs. Okay. This is the first remark. Then the second remark. Why do we have high Clifford index? So, for example, if rho of x in y is simple 4-to-1 cover of a general curve y of genus G, with ramification degree delta greater or equal to, well, we can of course take the ramification degree as high as we want, and we take greater or equal to 24 times the gonality of y, then it's not difficult to see actually that the Clifford index of x is greater or equal to 2g minus 1. So it can be arbitrarily high, Clifford index, right? Goes to infinity, but of course the genus also goes to infinity. Right? For the proof, one uses Castelnuovo's, it's easy consequence actually in exercise, just using Castelnuovo's inequality, which says the following. Suppose you have two coverings, x to yi, for I of degree ni, of degree ni. Then the genus of x is lesser equal to n1 minus 1 times n2 minus 1 plus n1 times genus of y1 plus n2 times genus of y2. This is the inequality. If you use this, you see immediately that the gonality has to be big, and then there's a relation between the gonality and the Clifford index. They differ by 1 actually, but this one has to go. Okay? So we get arbitrarily high Clifford index. Then one has to show that the coverings C1 over X, C1 tilde over C, they are different, right? So third, have to show that, Ci tilde over Ci is not isomorphic to X tilde over X. Right, so that we get really different things, right? Donagi's argument is interesting. Actually, that's what I like. Argument is the following. The monodromy representation pi 1 of B, so P1, well, in this case P1 minus B1, where this is the branch locus, with a fixed point here, into W of D4, differ by an auto-automorphism of order 3. These three, right? Two ones. Differ by an auto-automorphism of order 3. Actually, the group of auto-automorphisms of this is of order 3. And this gives you just the 3 other ones, right? But two coverings corresponding to the monodromy representation are isomorphic if and only if they differ by an inner automorphism. So they are non-isomorphic, okay? One could use this argument also in our case, because it also works there, but we do this by specialization. We specialize in such a way we get coverings with singularities, but then the coverings are different, one sees, so they have to be different before. So we do this by specialization. Actually, also because this argument couldn't really follow why this is differ by an auto-automorphism. This wasn't clear to us actually. Okay. So now let's come to the proof. Yeah. The point is, what we use is actually this correspondence, right? The other proofs don't use explicit correspondences. So let S be as above, and let S transpose be the transposed correspondence. I said already that I gave this definition here. A correspondence is a divisor, effective divisor in a product of curves. But as one uses it, it is actually S is, now I'm in C1, I don't omit this, okay, goes into divisor group of order 4 of X tilde. By just, if Z, you have a point here, the points were of the form X1 plus X4, you associate just this divisor, right? So here we look at it as a point, here we look at it as a divisor, right? And then one has also the transposed correspondence. The transposed correspondence you just get if you switch this, right? And then you get a similar way. You get a map from X tilde to divisor 4 of C1 tilde. Just by, if x is a point, you take all divisors of degree 4 in C1 tilde which contain x. Some z with x is contained in z. Right? So one has to show, of course, that there are exactly 4 of them, right? But this is clear. If z gleich x1 equal to x1 plus x4 is one of them, the other 3 are just then also, and exactly, I mean, x1 prime plus x2 prime plus x3 plus x4 is one of the other ones. The next one is x1 plus, what is it? No, sorry, it has to, this is wrong. So, x plus x2, so if this is one of them, should contain x, right? Plus x2 plus x3 plus x4 is one of them. The others, x2, the others are, you can dash here, x2 dash plus x3 plus x4 prime plus x2 plus x3 prime plus x4 prime. These are the other ones. So there are exactly 4 of them. So we get also a correspondence here, right? So now, so we have 2 coverings here. I give a name now. This was C1 and this was Y. I call this F, the composed map, and similarly here, x tilde goes to x, goes to y. I call this G, this map. Then we denote by, maybe I should not, I can work out here. One has also the trace correspondence, TF and TG. These are the trace correspondences. Namely TF of Z is actually F to the minus 1 F of Z. So take all pre-images. Okay? This is a trace correspondent, and one knows that the corresponding homomorphisms of Jacobians are 0. This is important. They are 0. The trace correspondence goes to 0. Okay, then we have lemma 1, which says that for all z in C1 tilde, we have S well, one can compose correspondences, right? By just, you know, you map this to this divisor, and then you map this to the divisor with S and all of them and add up, right? And take the corresponding. So you can compose this. And one can work out, this is actually 2z minus 2 sigma z plus 2 times the trace of f. Right? And similarly, for all x in x tilde, we can form this. And we get 2x minus 2x prime here plus 2t g of x. The proof of this is just a matrix computation, right? If you have this here, you can, you know, you have the, you fix a point here. Fix a point here. Over this are 8 points. You fix a point also here. Over this are 8 points, right? And the correspondence depends only on how these 8 points vary, because by monodromy you can change this, right? So it's given by an 8 cross 8 matrix. You label these fibers and label the fibers here, you get a matrix. And this matrix, I don't want to give you the 8 by 8 matrix, but it's a very simple matrix, right? And then you work out, you have a matrix equation here, right? You work out this and get this, so it's just a matrix equation. Very simple matrix equation. So you just show that the corresponding matrices, well, actually this is S transposed S. Actually the matrix is symmetric, so that you get the same here. And this is why this looks very similar here. You get 2 times the identity matrix minus J, where J is the matrix corresponding to the involution here, plus 2 times T0, and T0 is the matrix with ones everywhere. This corresponds to the trace correspondence. So just compute this. You have explicitly the matrix. It's very simple to work out. Compute this and you have this. Okay? So the next lemma. Is lemma 2, also a matrix computation. First, S, now this is the endomorphism of F star J of Y is contained in F star J of Y. And similarly, S goes from the prim variety to the prim variety, if you restrict. Okay? And similarly, the other one, S transposed of G upper star JY is contained in G upper star JY. And moreover, S goes from the prim variety of X tilde in X into the prim variety of C1 tilde over C1. Of course, the same for C2. But
S transpose.
S transpose, thank you. Where is the S here? Okay. Again, this is a matrix computation. We have to show this. We have to show that well, if these are the matrices now, S T0 is equal to T0S, right? And then we show this is actually 4T0, right? This implies it. Okay, just by looking now at the corresponding, you have the maps for the corresponding correspondences, and then this gives you these maps. So we only have to show this because this is automatic. This is a complementary abelian subvariety. Then this is automatic. Okay? Okay, from this we have proposition 1. S and S transpose restrict to isogenies S of prim variety. See, here we had only homomorphisms, but these are actually isogenies. C1 over to P x tilde over X, and similarly S transpose P of X tilde over X goes to P of C1 tilde over C1. Okay, and moreover, satisfying an equation, and this comes from the equation which I have here, actually, satisfying the equation, satisfying S transposed S is actually 4 times multiplication by 4 on the prim variety. Which one? S on P of C1 tilde over C1. And similarly, in the other case, S transposed goes from, is equal to 4 times prim variety of X tilde over X. Right? Well, the proof, how we get the proof? Is just that S transposed S is equal to 2 times 1 minus sigma restricted to P, according to this here. This is 2 minus sigma, and this gives 0 on the end of on the Jacobian, and since it restricts, we get this. And this here is on the prim variety is an isogeny. Okay? Because multiplication, this is an isogeny. Okay? This is all. So this is a proof already. As a corollary, we get degree of S of, well, every isogeny has a degree. Degree of S of P of C1 tilde over C1 goes to P of X tilde over X is equal to the degree of S transposed of P of X tilde over X goes into P in the opposite direction, C1 tilde over C1 is equal to 2. Is equal to 2 to the 2 dimension of P, of course, which is actually equal to the degree of 2 restricted to P, right? Because this is just the number of P of 2 division points. Okay, and this follows because proof again, I can write one on S transposed and S are transposed to each other, so have the same degree. The composition has degree 4. Did I write this somewhere? Yes, 4 times, right? One has to, I mean, cheat a little bit here because we restrict and then it has to stay 2 degree. Anyway, that's okay, right? Have the same degree. So have R transposed. So have the same degree. Okay, so now we need one more proposition, that now we have this map here. C1 tilde over C1 by S goes to P of X tilde over X. And the proposition is that this factorizes over 2 times P. P is this here, right? Factorize over 2 to C1 tilde over C1. With here we call this psi. So the proposition is that this factorizes. This proof is also elementary but a little bit more difficult. I have not the time to do this. What you do, you take the principal polarization here, pull it back and pull it back, and pull it back and see that it factorizes here, right? So one shows that the polarization factorizes, and this is here really by the alternating form corresponding to the polarization, so everything is over the complex numbers. So we have the polarization is also given by an alternating form, which I did not explain in my course and do not here. So this is all, but all is very elementary also. Doesn't use any complicated results on abelian varieties or so. But if we have this, we are finished. Then we can prove, right? So proof of the theorem. So the corollary says that degree of S is equal to the degree of S prime, F transposed, is equal to the degree of 2 restricted to P. Moreover, so the degree here is the degree here. So the degree of this has to be 1. So it has to be an isomorphism. Okay? That's what we want to show. Right? So this is isomorphic to this. So that's why I said in the theorem it induces, this S induces an isomorphism. Actually, you have to go down here and then it induces an isomorphism. So this implies that degree psi is equal to 1. So psi is an isomorphism. And since we saw that we just proved this by pulling back the principal polarization here goes to the principal polarization here. So it's really an isomorphism of principally polarized abelian variety. So thank you for your attention.